Good morning, everybody. Okay, so let me introduce my team member, Tuan Yuen, who is a partner in crime in this effort and initiative that we are undertaking here. So welcome back for some of you that were here last year that we talked about the cell-site gateway router. I'm very proud to let you know that if you follow the press, we have deployed the cell-site gateway router that we were here contributing last year. So thanks to the community and everybody that worked together that make this possible. So today, I'm going to present the AT&T is contributing the distributed disaggregated chassis model router. It's a new paradigm how we are building a chassis router from the traditional, way that we used to buy router that deploy in the carrier network to this new model. Okay, so what is it? For a service provider like AT&T, we need to deploy a large router, at the core layer where we call it the provider router, P-core, that's what we call it, at the center of the core. And then we have the edge layer where you deploy a lot of provider edge router for the different function and services that we support, VPN, internet, etc. And then on the outer layer, the aggregation and the access layer. So the focus today is we're going to talk about the disaggregated distributed chassis that we will be contributing, the specification that we'll be contributing for the core and the edge layer. Okay? Okay, so what is this about? As I said, right, traditionally, service provider like AT&T, we deploy, large chassis router that is monolithic, that's built by the traditional ODM. And what you are seeing here, this chassis chassis is that all those top on the top there is all the line cord that you plugged in. That's the front wheel, and then on the back, the horizontal line cord there, those fabric line cord that you plug into it, right? So functional, and then the top you have the common component like the the fan tray, the air filter, and the power supply at the bottom. So all this function you still need when you build a disaggregated router, okay? So what we're going to talk about today is how we are disaggregating it, and we'll construct that. We keep the function of the router the same, but how we go about doing it, implementing it, that is the essence of the new paradigm, okay? Let me see. Okay, so the disaggregate. So you saw in the previous slide where we have physically we have the line cord and we plug into the chassis. Depending on the implementation. The one that I was showing you earlier, it was the fabric cord on the back. So you plugged it in like that. Here, when you build the disaggregated chassis approach, we need to have all the same function, right, that we use to build a monolithic chassis. So how do we maintain that? So we would do consist of all the different module, the basic function, the module where we show like the green module there is the different line cord that you saw in the previous slide where you plugged in. So the module 0 to 1 and 1, 2, and 3, that could be different line cord of different speed, okay, 100 gig or 400 gig. And in the middle, analogous to the previous slide, where you have the fabric cord in the back. So this will be a standalone piece of box that there's a fabric, a line cord that allows you to plug the, interconnect the different line cord, okay? And likewise, so what I'm showing here is the different cabinet, 1, 2, 3 above, is that how you would physically, instead of like sliding the line card into a chassis, you would, install the pizza box in a chassis and interconnect them, via optical cable or DAC cable via the fabric module. And in this way, you maintain the same functionality. Then you might ask, well, where's my, what you call the route processor or the control system? So that will be like on the purple box there is your management switch that will connect to each of the line card. And the management switch, connect to the CPU, the route processor that will control all the routing and the control plane. That's how that's done. Okay. All right. So as I mentioned, what are the key components that make up of this disaggregated distributed chassis? The components are, we call it the spec called out for like the white box number 1 is a 2RU 40 by 100 gig port. With 13, fabric ports that allows you to connect it to the fabric white box, right? And then the other one that we have is a 10 by 400 gig port. Likewise, you need the 13. You bring out the fabric port so that you can connect to the fabric chassis. And then the third one here, the white box 3, that is a cell-based fabric white box. To allows you to interconnect the line card system. The other one that we also like the 3 and the 4, they are of the same functionality. It's just that the white box 3 has twice the density as the white box 1. So it's kind of like, think of it like functionally it's half of it. So it's 1 RU. Okay, so we're going to go through the spec of all this white box. Oh, and then the other thing that I want to point out is that we also need to support the breakout mode because all this like bring out as a 100 gig port, but we do want to support some of the 10 gig ports so that we can have backward compatibility for other systems. So in the spec, we need to, for that, at least for our application, we see that would be a good advantage to have the breakout. So in the design, we need to do that. Okay, so pictorially, this is, the different white box 1, 2, and 3, and 4 that I described earlier, and they specify the dimension. Basically, for 3 of the 4, it would be 2 RU because of the thermal consideration and the density that you need the real estate to bring out all the phase port. So it's 2 RU, and then the one that for the cell fabric chassis, it would be half of the, which one is that? It would be half of the top one, white box 3, right? So white box, no, the 4 would be half of the white box 3, right? Yeah. So, and in terms of the cell fabric connection, the type of cable that need to be supported, we support like the DAC option, the AOC cable option, and the cable length, there's some limitation. So we'll provide the spec in the next slide. Okay, there's some maximum distance limitation, right, where you can have this like 100 between when you connected the fabric port from the line card to the cell site fabric switch is 100 meter. Okay, and let me see what else that okay, and then the other thing to call out is that then you have the craft interface RJ45, USB, etc. That need to be supported. And let me see what else. Yeah, and then I have to support the the chassis beacon as well. And we specify the different down to the LED color, what green, yellow. So it will be detailed in the detail specification. Okay. Okay, so as I mentioned, here's like the major requirement it need to meet, because this is for service provider central office deployment. We need to meet the 76200 level 3 for the central office telco environment, and we also plan to deploy this box globally, so it need to meet the most of the world homologation requirement as well. And the physical dimensions, 1 RU or 2 RU, the standard length, height, and depth. Let me see. And the airflow is for our application, it needs to be front to back airflow. And they need to have like hot swappable fans and power supply, 1+1 redundancy. It need to support AC or DC power supply with high efficiency, 80 plus or better. We asked for the circuitry to support 1588V2 and SYNC-E with transparent clock, the boundary clock, etc. on each of the box. So you need to have the circuitry that provision there to support it. And in terms of the disaggregated distributed chassis synchronization, among all the boxes, that is an item, for future work and collaboration. And we look to the community and everybody to help, look into that area. So that is an item for future development. We will have an onboard BMC with dual flash. We want to make sure that the BMC is an optionable factory installable option, and have the typical Intel x86 CPU with TPM but no coin battery, cell battery. We will be using the Broadcom Jericho 2 plus the HBM, the deep buffer. We will have the OP2, which is the TCAM for high route scale, right? Because application, this is for a provider edge and core router. So we'll do that. And then the Ramon, we use the Broadcom Ramon for the fabric white box. Okay. This slide just shows a physical dimension to make sure that there's enough clearance and cabling, because with the distributed disaggregated chassis, there's a lot of cable that run between the line card to the chassis white box. So we want to make sure that you can't just squeeze everything together, and when you try to put it together, you cannot route the cable. So it's very important, that we meet all the clearance and physical dimensions. And then one of the key requirements is that the rear mounting need to be adjustable, so that when people install it, right, you have that flexibility to make the adjustment as needed. Okay, so this is the high-level block diagram, the design, and as I was mentioning, the dual power supply and the fan. From 0 to N, whatever that's needed, so that we can meet the thermal requirement. And this is, as you can see, the key component is the BMC, that is factory installable option, x86 CPU, the Jericho 2 Mac with HBM, and then also the OP2 to support high route scale. And then on the corner here is all the different craft interfaces that we have to support, including the two 10 gig E, from the x86 CPU that we bring out to the SFP. So those are like for network management and other use. And then this is the 40 I/O port that we bring out, and the 13 fabric port that allows you to connect to the fabric chassis. Here we specify the the port numbering is very important because you need to clearly specify that so that the NOS provider that developed the NOS, will work with this, because not everybody uses the same convention, okay? And so we want to be very clear that specify, from 0, it start with 0, and then how we number it, on the 4 row. If you look at the physical port, you will have like 4 row of I/O port, and the numbering and how you silk screen it, we want to be consistent so that it's standard and everybody build to it. And, in the future, you can leverage the white box. Or otherwise, everybody build it to their own numbering scheme, and you won't be able to use the white box interchangeably. Okay, so little minor detail there. And at the bottom here, we're showing that when you do the breakout to 4x10 gig, because of how all this, the Jericho 2 is run on the 50 gig SerDes. So when you do the breakout, you kind of like have to sacrifice the other port will not be used as 100 gig. So just want to point out there. Let me see what else. Yep, I think that's it. So this is the line card, right? Likewise, for the line card that is 400 gig port, what you have is like the I/O port, will just be 400 gig versus 100 gig, 40 by 100 gig port that I showed earlier. But in terms of the functional block and key component to support the 400 gig port is similar, right? So the main difference is if you look at the I/O port, instead of like 40 port, now it's 10, 40, 400 gig port. And then the fabric port, same, is the 13 of them. Okay, so this is a functional block diagram for the cell-based fabric white box. Okay, that allows you to interconnect the line cards. And likewise, we follow the same, convention, the port numbering scheme. The difference here is that this one has 2 Ramon fabric chip instead of the Jericho 2 MAC chip. All right. But in terms of the craft interface, etc., is similar to the one for the line cards. Okay. This one is similar to the previous one, except that instead of the 2 Ramon chip that provide 48 ports, this one is 1, and it provides 24, just half the capacity. All right. So this is some note that we want to call out on the cell, fabric connection. Will support, the 400 gig QSFP optic, fiber, and the length of it is 100 meter max. And then we'll support the DAC cable as well as the active optic cable as well. Okay, the 100 meter max is a Broadcom fabric latency constraint, so we want to include it here so that we don't want to run the cable that exceeding that. Okay, so how do you? This is a logical illustration of if you were to build. So this disaggregated distributed chassis, right? You can think of it like the smallest unit would be like 1 line card box. You can scale it out, build it up to, depending on how large of the cluster that you want. You can build it from 4 terabit on a single pizza box to, let's say, the large size, about what called the large size, 192 terabit with multiple, I think it's up to 7. You just have to figure it out, the fabric port and add it up, right? So the size that you build, And the number of fabric chassis that you need is depending on the size of the cluster that you want, right? Because you have to do all this interconnection. So this one showed that if you want a 16 terabit cluster, you would need four line card pizza box line card, and you would need that connected, how the fabric port, from each of the line card have to connect to the fabric pizza box and interconnect, so you build this large system. Okay, if you need more capacity, the cluster to be larger, you will need to deploy more fabric connection blocks, just so that you can connect them up. Okay, and it shows you how the RP is a route processor. So you have a dual, route processor 0 and 1. So that is run separately and then connected to the management switch, and the management switch connected to each of the line cards, so that the route processor can talk to and manage, right? Do the routing and control and forwarding. All right. So all this component, what we would consider as, this is like a distributed, disaggregated distributed router, right? That I showed in the previous slide, where you have just one router. But with that one router is whatever the capacity you get. Whereas this one, you define it up front, what capacity that you want, and you build the size of the cluster accordingly. So that this way, you have all the basic functional block to allow the Lego building block to allows you to build, the size that you want. So it's modular design and it's scalable. It's you can scale it out. Okay, so this is a example of if you want to build even a large cluster, what would you do, right? Then you just have to deploy more fabric white boxes to allows you, so that you get enough fabric port to connect each of the individual line card. Okay, so so it's a lot of in this way, you really have to be careful in doing the connectivity design and the laid out design. So that's important and critical, because you have to plan, right? It's just like when you buy a house, you want 5 bedroom, 4 bedroom, you have to kind of do a blueprint and plan it out. And then once you have that, you can, it's modular in the sense that maybe day one, you don't need to deploy all your line card, right, as you need, but you need to plan the footprint for it, the connectivity. So as the demand need, you just plug in the additional line card, the chassis. Okay. These are the craft and console port that I showed earlier. We need to have a micro USB, serial RJ45 USB port, and the two 10 gig ESFP plus port that I showed in the functional block. For our band management and for the console support, and the two 10 gig ESFP port to provide connection to the x86. So that will be used to for the route engine controller to talk to the DCC. Okay, and this is only needed when this one is when you build it a cluster, right? If you just use it as a standalone box, you don't need that. Okay, so as I was said earlier, although we asked to have the 1588, timing function circuitry on each of the on each of the pizza boxes in the line card, one of the things that we really need to work on with the community is how to do the timing synchronization for a distributed system like this. Because right now, each one, yes, you can have that as a standalone box. It will support 1588. But on the distributed system, how do you distribute timing, across all these boxes? So that's something that we should work together, and we welcome, everybody's, idea. And as a community, we need to work together to develop the spec that will be, workable for a distributed system like this. Okay, I think that's all I have. Any question? Yes?
I have a question. On that last slide, Jenny, you said...
for the recording.
The last slide you had, on the top there, other ODMs to build J2C type configurations. Now, the J2C is heavily oversubscribed. If you make a 40-port, 100-gig version of that, are you suggesting to oversubscribe the core router on the Leafs, or have lesser front panel 100-gig ports on that?
Yeah, that is a good question, because for Jericho 2C, we are not, typically for the core, we don't really oversubscribe, do any oversubscription. But for, other use cases, it's more like maybe for the Leaf, right? That then you might, either that, for the Leaf, you can do the oversubscription, because typically for any typical application, you don't really, exhaust the Leaf. So there we probably need to, I suppose, you bring out all the port, right? And if you use the application for the Jericho 2C, the port, then you can build the engineering rule that to say that, well, look, although there are all this available port, you shall not, right? Depending if you really want to use it as oversubscribed, okay? But then there's some cost associated with it, right? If you're gonna bring it, that is the trade-off, right? If you want to build a kind of more versatile boxes that can use many applications, but then if you use it for the P core and you don't plan to use oversubscribe, you kind of added the cost to it unnecessary. Mm-hmm. Okay. So it's trade-off, right?
It's designed to use as an edge router, for instance. 2C is probably very good for the edge.
Okay, so maybe the
it's more like
2C
for the edge
Leaf at the edge,
case.
but not in the core.
Yeah,
Yes, you're thinking. Okay.
Yeah, yes,
okay.
right. But it would not prevent you from using as a, if I would just do the development for that, but then you have to set engineering rule to not oversubscribe, or unless you want to run, very aggressively, you can still oversubscribe, right? It's just we typically would put engineering rule, for cases like that. If I were to use it for the core router, I would put engineering rule to say that only, I don't know, X minus some number of port should be used.
The advantage of the 2C is that you have one core, but you have the whole 52. So you double the route scale,
Right.
you double the count. It's very good for it.
Yeah. So for the X-Leap application, are good.
Mm-hmm. Mm-hmm.
Not for, or like BNG, for example.
I have a question on the cell
Yes?
part.
Yeah, the cell base.
Yeah, so, in the typical model where they're sprayed
Across the, yeah.
and that goes to a line card that has some packet memory, and then they're reassembled on the output, the egress line card. The cells are reassembled again.
Yes.
On the way out. So one question is, have you given any thought to the cellification of the packets?
Right.
And then what type of protocols are you thinking for the multipath through those cell fabrics? Are you planning on having a cell header, or are you just going to, we'll make very small IP packets that are our cell and then use some IP routing protocol through that.
But the fabric, the Broadcom Ramon chip, right? So we don't really specify that, like, so that's why, right? So the Broadcom Ramon chip does the magic. Okay, so we don't have any.
Okay.
So when the packet come in
So how does that
ingress.
interact with the Jericho though? Or the Jericho sends an entire packet to the Ramon and then the Ramon cellifies it? But that's the forwarding chip that's in the cell fabric.
The Jericho
No.
2 sprays the packet over
Yeah.
available packet, so it brings it into cells. But it's
Okay.
internal to the
It's internal, yeah.
Broadcom,
Okay, so
It's
it's an internal Broadcom protocol.
Yes, protocol. Yes, it's a Broadcom
For spraying the
Yes,
cells
for
through.
spraying it across. Yes,
Okay.
and then on the egress, it reassemble it.
Yeah,
before.
and so is there any the packet buffers for, or in this case, the cell buffers, not a packet buffer.
Right.
But where are those, or is everything, is it able to deliver all those cells at once through the fabric, or is that what you're talking about? Your engineering rules to the oversubscription?
Well, so with the Jericho 2 chip, right? Although the chipset specify like 4.8T, but the way that I think that it perform at the line rate at certain specified packet size. Okay, so in order to achieve that, certain packet size with that, we actually only use like 4T, right? 4T out of the 4.8T to achieve the 100%. We tested for 100%, line rate. So if I were to and that's why we only bring out like 40 port. Yes. For the port, yes.
Okay.
that's why we asked for that. But the packet size, I think it's around
286 or something like that. It's the
286 by
minimum
cell.
packets.
Okay, now you're talking a packet, not the cell size.
the packet size.
What's the cell size that gets cut into?
That's internal. We don't care. We don't know, right? We just ensure.
Okay, so how are you gonna? Okay, I don't understand when you say you want so your minimum packet size is line rate. Okay, is that a fair? From what point of view is that? So if you don't know the cell and you don't have control over the cells, how are you going to guarantee that
Well,
rate
if you look
through?
at the cell, right, you have 13 gigs.
Port.
So you have more cell bandwidth.
The incoming.
So it's guaranteed to do line rate.
Okay.
So
Okay.
Yeah. Any other question? Yes? Hi, Winnie. Oh, okay. Winnie.
The last page you say you are encouraging to the vendor to do the Jericho 2C, but do you encourage other vendors to do the same design? And when will be the deployment time frame?
Yeah, I mean, so for us, AT&T, we don't really have a deployment timeline for Jericho 2C, but the similar spec that we specify for the line card, right? You could, the next generation, depending on the application, especially for X-Leaf, right, or the Edge, you could also use a similar spec to develop it using the Jericho 2C.
Oh, I mean the Jericho 2 plus Ramon architecture. When will you start the deployment? For the existing
for the
one?
Jericho, the one that we
Yeah.
are. So we are in the lab in development right now. So it's probably next year. So that's in development phases right now. Yeah. So any
Yeah, I have a really quick question.
Sure.
Have you done any sort of cost comparison, say on a per 100 gig port basis versus equivalent Cisco or Juniper offering, to see if is it a
yeah,
lower initial
yes.
capex and
I think that the answer is yes. We have, and it is it's cost advantage, and it's really capex wise. It is a lot lower, and we also use third-party optics. Okay, meaning that right. So it's really we totally embrace open ecosystem and use that. The answer to your question is yes.
Yes, okay.
Otherwise, I don't think that. We have to do a business case analysis, etc., in order to get on this journey.
Thank you.
Hi.
So just following on from that,
Yes.
why do you need third-party optics if you've got white box open source connectivity?
Well, when I say that third-party optic, I meant previously, traditionally, we would buy optic from some branded supplier or something. Whereas
From Cisco or from
yeah,
Juniper?
from Cisco, Juniper, or some branded one. But whereas the way that we look at it is now with the open source, I think that 2 years ago, AT&T start writing spec for optic, etc. So we are certifying optic as long as the optic meets requirement, performance, and meet our certification, and then that all our candidate we would consider.
So
right? That's what I meant.
Okay.
Yeah,
all
so
right.
it's really play the equal, likewise with the white box, right? We really want to make this all, open.
Okay, understood.
Okay, any other, yes? Hey, Paul.
Test. Okay. I believe to have understood from other sources that the possibility to get from a packet from the data plane into the control plane, into the x86 CPU, via the PCIe connection, the control connection is inefficient in comparison to a native connection via the 10 gig base XR connection that is available from the CPU board. So I see from other designs that there's a direct connection from the switch chip to the x86 and not getting them out on a SFP transceiver to your central CPU switches there.
Okay.
Have you any thoughts on this?
Yeah, Jericho 2C the Jericho 2 doesn't have those extra 10 gig
Right.
port like some of the other chips.
Yeah. So we cannot connect it directly.
Would require a gearbox.
Yes.
Okay.
We wouldn't have lost the
That might have the same question related. You asked this question for the synchronization architecture that to be employed by such a setup. That was the reason for us to provide a gearbox for certain of those 25 G SATA lanes to have the possibility to have a 1G 1588 Grandmaster clock input. So I wonder if you want to run in the same issue and maybe would be required to have something like a SATA, like a gearbox chip to have the possibility to have ingress for a Grandmaster clock at lower rate.
Lower than 10 gig? Okay. All right. So
not even lower than 10 gig because you wouldn't have even the possibility, as I understand, to have lower than 100G. So I don't think it's a good idea to have a 100G Grandmaster clock distribution system.
We do have in this design reverse gearbox, right, and the line card in order to to support the
but not on all systems. For the 400G systems, I don't see any way to get in to a Grandmaster clock.
Yes. Yes. That.
Okay.
It's another switch chip. Yeah.
Right now it comes straight out to the front panel.
Yes.
Okay.
It's possible to put
Yeah, inside.
Okay, but it was not in your drawings yet,
That,
right?
no,
Okay.
not that. That is good observation on the, yes, for the 400 gig, yes, that's
Okay,
correct.
thank you.
Yep. You're paying attention.
Any other questions? Okay, if not, thank you,
All right,
Janet.
Okay, thank you.